Hey guys, welcome to our YouTube channel. First video.
Today we'll be covering Unit 1 of AP Chemistry.
Topic 1.1 Moles in molar mass.
This kind of mole.
It's a very large number of particles that has approximately 6.022 times 10 to the 23rd amount of particles, molecules, whatever you want to do. But this is called Avogadro's number.
We do this because atoms or molecules cannot be counted directly.
So how do we even convert and try and use this number? Okay, so when we're trying to convert from mass to moles, we need to use the molar mass. And you can either multiplying by the molar mass. So you can start anywhere from mass, you can start at moles, and you can start at number of particles. And this is basically going to get you the amount of stuff that you have in your, certain compound. You might be asked to find the mass, you might be asked to find the moles, or you might be asked to find the number of particles. In order to go from each of them, you can use this helpful little system. If you're going from moles to mass, then you multiply by the molar mass, but if you're going from mass to moles, you divide by the molar mass. And then same thing for Avogadro's number, but from moles to number of particles, and number of particles to number of moles, which is pretty cool. So for example, if we have 0.85 moles of carbon, then we're gonna multiply by the molar mass. Oh my goodness. 12.01 grams carbon. And then we're gonna be able to get the mass of carbon up to 10.21 grams of carbon, which is pretty cool. Don't forget to put in all of your units because that'll be really helpful, especially when you're on the AP exam and you're on a time crunch. You're gonna wanna know what goes where. So that's pretty cool.
Mass spectroscopy.
Despite its complicated name, it's actually my favorite part of AP Chemistry because it's easy. So here on the y-axis, we'll have the relative abundance, which is how abundant this element will be in the real world. Down here, we'll have the atomic mass, which is of the element, which will be the number of protons plus the number of neutrons. The line on this graph will represent a different isotope that you can find in nature. Because each of these peaks represent a different isotope, we can use this information to find out which element this will be.
Now we're going to talk about pure substances. This includes both elements and compounds that always have a fixed composition. This means that this sample of water, hydrogen and oxygen, will always have 2 hydrogens and 1 oxygen.
So what if we want to find the mass percentage? So first we want to find the total mass per element. Then we want to find the sum of the masses to find the total mass. Then you divide the individual mass by the total mass. Lastly, you multiply each value by 100 to find the percent.
So what about when we have no clue what the substance is, but we have the percent composition? Well, lucky for you, my teacher, shout out Ms. Check, has a little poem. Basically, it goes like this. You go percent to mass, mass to mole, divide by small, multiply to whole. This works practically as you go from percent to mass by simply changing, instead of a percent sign, you change it to a grams. And then you go from mass to mole by going from the grams to the mole. Then you divide by the smallest number of moles. So for example, if there was a 0.3 moles and then there was a 0.02 moles, you divide that 3 by the 0.02 and then you get a really big number. And then you multiply till they're whole. So sometimes you're gonna get like a 0.5 and you're gonna wanna multiply that until it looks around like a whole number. You might get like 1.998, but that's basically 2 at that point. So let me show you a practice problem to make it a little bit less confusing. Okay, here, starting out, we have 13.5% Ca, 10.8% O, and then 0.675% H. So we're just going to go, remember, percent to mass. So change all of these to a gram symbol. Then from mass to mole, you guys remember to divide by small, and the smallest number here is the 0.337. So we're going to divide all of these by the 0.337. So then when doing this, we found out there was 1 Ca, 2 O's, and 2 H's. So the final formula would be CaO2H2, which can also be written as CaOH2. Pretty cool, right? Pretty cool.
Wrong!
Matter can be separated into 2 different categories, pure substances and mixtures. Pure substances are like their name, pure. They only have one substance. Pure substances, we have elements, which are composed of only one type of atom, and then compounds, which have 2 or more.
You are all failing your AP test. Anyways, moving on, we have atomic structure and electron configurations. This is an atom. We've got the core electrons, and then we've got the valence electrons. The valence electrons are in the outermost energy level, and these 2 things are energy levels. Then we have the nucleus, which is positively charged because it's composed of both protons and neutrons. The protons give it that positive charge.
Sorry for the outfit
moving
change.
on, we have our electron configurations. It's basically explaining what's happening in the atom. So we write it something like this. It might look a little bit confusing at first, but the 1, 2, and 2 mean that's the energy level. So this one's going to be the first energy level, this one's going to be the second. So within these energy levels, we also have sublevels. So this one's the 1s 2 sublevel. The S sublevel can hold 2 electrons. The P sublevel can hold up to 6 electrons. This one's just the electron configuration of nitrogen. So the little 2 means the number of electrons in each sublevel. So you have to fill all of your bottom sublevels before you can fill the last sublevel. And it goes 1s2, 2s2, 2p6, 3s2, and so on and so forth. It's a little bit confusing, but there's a little trick to it. So here we have this little thing. So it shows you how it goes from 1s2 to 2s2 to 2p6, 3s2, 3p6, 4s2. So you might be wondering, like, oh, why does the 4s2 come before 3d? Well, it's because you need to fill those ones. And it'll still, if you're still removing an electron, it would still be removed from the 4s2 before it would be removed from the 3d, but it's all about where it's placed on the periodic table and everything. And next, we have Coulomb's law. It's really big because it's very, very important. Especially on your AP test, you're going to be asked to justify things in terms of Coulomb's law or, like, according to Coulomb's law. It's basically the law that you use to figure out whatever. I'm done. So Coulomb's law states that the greater charge equals greater force of attraction, and the greater the distance equals a weaker force of attraction. So this is basically like if you have this versus this. So it's if an electron is right here, the force of attraction is weaker because it's got a greater distance from the nucleus than this one. And then the greater the charge would mean like if I have an mg plus 2 versus an mg. Since this one's got the greater charge, it has the greater force of attraction. So like if this mg was placed like with an O minus 2, for example, this one would be greater than this one, even though there are 2 mg's over here. Now back to my weird little drawings of little atoms. So now we're talking about ionization energy. Ionization energy is explained by Coulomb's law, so I basically explained it, but now I'm giving it a name. So this one's going to have a greater ionization energy than this one. It's basically the energy that it takes to become an ion. So to become an ion, you need to remove, in this case, I'm saying they need to remove an electron to become. If I'm removing an electron, then it's become more positive and therefore having a greater charge. So then this one's going to have lesser of a distance from the nucleus, so this one's going to have a greater ionization energy because it's going to take more energy to take away an electron. This one is going to have a lower ionization energy because you see all these sublevels? It's shielding this nuclear charge from this electron, so it's not getting as much charge. Okay, so what the heck are we looking at here? Here we have I forgot what it's called, a photoelectron spectroscopy graph. Despite its complicated name, it's actually relatively simple, except I struggled with this on the AP test, but I'm doing this so you guys don't struggle. So on the y-axis, we have the number of electrons. As you can see here, each peak represents the number of electrons. So as you can see, this sublevel holds 2, this sublevel holds 2, this one holds 6, that's why it's higher, this one holds 2, but this one holds 6, but it only has 1 in it right now. You can see that because it's half of that peak. And then, thank you. Anyways, so on the bottom we have binding energy. So as you can see, it will have, this one would be like 6,000 kilojoules, and this one would be like, I can't think of another number, like 6,000, nope, like 5,500. So as you can see, this one will have a greater binding energy than this one, because this sublevel, remember, is on the outside of the atom, like I was explaining. Next, we have valence electrons. These are used to determine the likelihood of two elements will form a bond. So the valence electrons are the electrons in the outermost sublevel, and then those are the ones that you're going to be able to take or add to, because all atoms want to reach a full octet. What is a full octet? It's 8 valence electrons. Everybody wants to reach that because they're stable. So for example, neon already has 8 electrons, so it's not going to want to bond with anybody. Like, you're never going to see, not never, but you're not going to see on the AP test an Ne trying to form a bond with an O. It's just not going to happen.